Hi, guys. We're going to go ahead and start our unit on the normal model. Very, very, very like fundamental stuff in statistics. Um, yeah, even more so than standard deviation. Of course, you got to know standard deviation to be able to do normal model. Okay, so I want to kind of walk you through just where the history and what's kind of happening and where it's coming from. So first, what's happening is we're going to use the normal model to find probability of events happening. And when we are able to do that, then we can talk about if something's unusual, wow, why did that happen, those kinds of things. And then that takes us and allows us to do lots of statistical tests and draw inferences. Okay. But first, I want to kind of talk to you about where this idea of calculating probability with this normal model thing, what that is, comes from. Okay, so here we go. So, first, when you have a probability distribution, the probability of something happening is actually the area of that event. So, let's take a look here. I'm going to show you some concrete examples first. So here is, it's a bar graph, I guess, because these are categorical, the sides of the die. Okay. Now these are discrete events. So that's a finite possible amount of things. Okay. Countable. So that's also, why we have this here. And so we could get a 1, 2, 3, 4, 5, or 6. Well, those are equally likely. So in essence, then we have this uniform or rectangular shaped object here. Okay. So if I wanted to calculate, say, the probability of getting a 3 or less, see, then this area here is of 3 or less is half of this area of this shape. And this shape, of course, represents 100% of the possibilities. Okay, so that's kind of that connection there. Here's another example. This is the different types of cards. So out of our 52 cards, since we have 4 of each type, that's 1/13 for each kind. And these are categorical, really. And so here we have the different categories. Equally likely. So that was uniform. So that's why we have then this rectangle. So I could say, what's the probability of getting a face card, which incidentally, face cards have a face. So that's king, queens, and jacks, not aces. Okay. Kings, queens, and jacks have faces. Anyway, so I could take a look at that and I could calculate the rectangular amount of that area there. All right. Now, here's an example of something that's not discrete. It's called continuous. And we're going to get more into this idea and this relationship between discrete versus continuous later. And we'll start identifying which things are discrete and which things are continuous and what's the difference and what's the deal. But right now, we're going to be going into these continuous probabilities. So that's why I want to bridge to something that looks like this. So this is infinitely many points on a dartboard, okay? Because that dart can land in such a small, infinitely small spot that you really have tons and tons and tons of options of how to land within this 1.25-inch circle. Okay, and so then these are the locations of this, and then the probability of getting those locations in that circle. Okay, so now they were equally likely to land in that circle. So then we had all of the probabilities at those distances the same. Whether or not that's true or not. Now, of course, this is probably talking about just the little red circle. Well, that little red circle is so small, okay, that it is probably going to be every little piece of it's going to be equally likely. Okay, so with that being said, let's calculate some areas, also known as the probabilities. Okay, so how would we calculate the probability of landing in the shaded area below? So this one on the left, we want to take a look at this. This is a rectangle from 0 to 1. Okay, and it's 1 in height. That's not marked there. Okay, we're going to say that it is 1 in height. And the reason it has to be 1 in height is because I know the area underneath here has to be 100%. So if this width is 1, then the height has to be 1. Kind of doesn't look like it. I wish I would have redrawn this picture to make it a square. Okay, so what's the probability of getting something in the red area? Well, we're going to calculate that. And we know how to calculate area of rectangles. So it's that length or base times that height. Okay, so I'm going to calculate that base times the height, and that's 0.4 times 1. So the area for this would be 0.4. So 40% chance when you throw the dart or whatever, you're going to land in that red area. Okay, looking at it over here, I notice that this x-axis is going to 2. So because this has to be 100% of the data, this x-axis is going to 2, therefore this height is 0.5. So the probability of landing in this, so this is at 0.6. So I need to calculate the area of this rectangle, of course. So this width here would be 1.4 times the height of 0.5. So we would have an area of 0.7. So there's a 70% chance of landing in that shaded area. Okay, now, so hopefully you can see then, that connection, that calculating the area is the same thing as its probability. And so we noticed that the total area for probability distributions is 1, also known as 100%. The probability that that event's going to happen is that 100%. Okay, now, therefore, the total area, what we call under the curve, now these ones that we just did were, the curve was flat across, so it was rectangular. So the total area under the curve is the same thing as its probability of that event happening. Okay, so now let's bridge from rectangles into more worldly data sets. Okay? So these histograms below are based on actual data. They're technically not what we officially call normal or whatever. So I want to make this connection between percents, that is the probability, your proportions, and those probabilities. Okay, so let's take a look at these pictures here. So here's a histogram, it has 7 intervals. Okay, so this, we could really calculate those rectangles. We could do that. Well, but the real data set doesn't look jagged like this. It doesn't just have these categories, that are from 15 to 19 or whatever those categories are, okay? Typically, if we have data, that is more discrete or continuous, then we need to have this smooth curve. And we want to calculate the area under this smooth curve, not this jagged, just 7 rectangles worth of area. So what happens is we start making smaller rectangles so that we can calculate the areas of those smaller rectangles. And so what happens is, as these rectangles get skinnier and skinnier and skinnier, you eventually have just all these little slices that you're going to add up. And you can add up those slices and you can get an actual curve to the feature instead of just jagged rectangles. Well, guess what? This is a continuous probability distribution. It's much more common than for real world, okay? In fact, we'll learn later how to get things that aren't normal to behave normally so that we can compute, okay? And so there actually is a mathematical function for this collection of data when it's distributed this way. And it looks like this. So here is your normal model, folks. All right, here is this function, and who came up with that function, I don't know, but we have this collection of data. So you can imagine these are histograms or little infinitely many teeny tiny bars, high, tall. So 0 events is this frequent, and the 1 standard deviation above the mean is this frequent, and so on and so forth. So you have those height of those bars. I went ahead and showed you that function in our calculator and then how that shows up on our calculator and what it looks like. All right, So we want to be able to, let's kind of just identify a few things about this. Okay, first of all, where is the mean and the median? And hopefully you can see that the mean and the median are the same because this shape is symmetric. Okay, now what do you think is going to happen as this curve, as the standard deviation gets larger? And so these little things right here, so the mean is centered right now at 0. Okay, and then this is one standard deviation over. Okay, and then a second standard deviation over. And then a third standard deviation over. Do you remember how when we said what outliers are with the standard deviation rule? Outliers with the standard deviation rule is these things out here past 2 standard deviations. So anything in those areas would be considered outliers. Okay, they are statistically unlikely to occur if the data is really centered here. Okay, so what's going to be the total area under this curve? If these are all the possibilities that can happen, the total area under that curve is 1 or 100%. All right, so now how many standard deviations are across the spectrum of the normal model? So I hope you can see here that we have 3 standard deviations above the mean and 3 standard deviations below the mean. So that's in total 6 standard deviations. Okay. Now, let's talk about this. Could we compute the area or the probability of finding something in between 0 and 1 standard deviation above the mean? So could I calculate the area of this, right here with our current methods that we know? Rectangles, triangles, trapezoids, circles, those kinds of things. Can we calculate the area of that shape right there? And hopefully you can see that no, we cannot. We cannot because of this curvature here up at the top. Well, that is where calculus comes into play. We don't have, it's curved at the top. No, the shape is between 0 and 1. We don't know those formulas. Okay, so calculus to the rescue. And you may think, oh my God, I don't know any calculus. I wasn't even in pre-calculus. Okay, well, that's okay. Because luckily, this function is something that's so common, it's normal model math. And so our calculator does all that calculus computing for us. We just have to know how to apply it and what that means. So here we go. Here's kind of what's happening in calculus if you happen to be in there. Here is the function from your data piece out to infinity or whatever. And what it does is this is integrating. So that is collecting all of the areas of those little individual slices, those teeny tiny slices of data to get that collective area of any shape. Okay, so that's what's happening with that calculus. So in summary, here's what we have. Let's go ahead and take a look kind of at this summary of the normal model. Okay, it is symmetric, it is unimodal. The area underneath it is 1. Look at how this is written here. A capital N, and then with these parentheses in what looks like an ordered pair, this would notate this is a normal model with a mean of this first number and a standard deviation of this second number. Okay? And so then here you go. We can see the mean, 1 standard deviation, 2, 3, and standard deviations up, 1, 2, 3 down. So now we're going to address these 68, 95, 99.7. So those numbers, 68, 95, 99.7, so 68 is this area here. This area within 1 standard deviation. Let me see if I can color it better. Let me see if I can color it better with my finger than the mouse. Okay, so this area within 1 standard deviation of the mean using calculus was computed to be 68% of the entire value in that curve, 68% of the 100% of data. Okay? Then if you go if you go 2 standard deviations out, then calculus came along and computed that this section here in its totality, from 2 standard deviations down to 2 standard deviations up, all of that area is 95% of the data. And then if you add these last little sections to 3 standard deviations, to that line right there, to 3 standard deviations, then you now have a total of 99.7% of the observations of the stuff that we're talking about. Now, there is a little bitty bit out here, and we're going to compute how much that is. So this is just like the way, oh my gosh, extreme outliers, extreme past 3 standard deviations out. Okay, so let's move forward. So this thing called the empirical rule, also known as the amazing 68, 95, 99.7 rule, is what tells us what calculus computed. That 68% of the data is between 1 standard deviation down and 1 standard deviation up. 95% of the data is between 2 standard deviations down and 2 standard deviations up. And 99% of the data is within 3 standard deviations down and 3 standard deviations up. Now, let's take a look at the curve that you have down there at the bottom of this page. We have this with our 68, 95, 99.7 rule, okay? And I want us to now segment out how much each one of these sections are. Okay, so for example, I'm going to be able to know just what that shaded area right there between 1 standard deviation down and 2 standard deviations down is. So I want to know how much area that is. Okay, so you can do that. For example, if we know from 1 standard deviation down to 1 standard deviation up, you have 68%, then I would know that 34% of the data is in that section right there, and 34% of the data is in that section right there. Okay? So now I want you to use some of your math skills, your algebra, your brain power. And so knowing that from here to here, we have 95% of the data, and that we already have this 68% accounted for in here, how can you figure out what is left in each one of those sections? I should probably show it down here below. How can we compute this section here? So let me give you a few moments to do that. Okay, so 95% minus the 68% is 27%. So the totality of this blue section is 27%. And so then if I take that 27% and I divide it in half, then that's going to give, divide it in half, then that's going to tell me how much is in each one of those sections. So that's 13.5% is in each one of those blue sections. All right, I want you to do the same type of computing and find out what is in each one of these sections here from 2 to 3 standard deviations down. And you're using this idea of the 99.7 is 3 standard deviations across. Okay, so compute that. Okay, so divided in half, you will see that each one of these yellow sections is 2.35%. Okay, because we had the yellow total is 4.7%. And so then there's that. So now we have a teeny tiny bit out here. So let's take a look at how much is actually out here in the pink past what is going past or what are extreme. Okay, so figure that out. Let's do that final calculating. Very little. So I took my 100%, took away all this in the middle, the 99.7% in the middle, and that's 0.3% make up those two pink sections. Divide that in half, and we have 0.15. So not even 1/5 of 1%. Not even a fifth. Point 0.2 would be a fifth of 1%. This isn't even a fifth of 1% chance of having data out here. So that's just how extreme we're talking about. The likelihood of data being past 3 standard deviations. So if you get something past 3 standard deviations, we're going, oh, holy moly, what the heck is going on here? That is very unusual, and that's telling us something. All right, so let's do this here. Assume the heights of college women are normally distributed with a mean of 65 inches and a standard deviation of 2.5 inches. So we would come here and we would then label this area, okay? And so I have already gone in here and I labeled it. So let me point out some features. I want you to put those standard deviations down. 0, 1, 2, 3, -1, -2, -3. And then label in context the other values, the context values. The height of college women in inches. And I said 65 is right here in the middle. And then, okay, so here is what's happening. So if I take this 65 and I add 1 standard deviation, okay, if I take 65 and I add 1 standard deviation up, that's how I get 67.5. Okay, and then if I add another standard deviation up, then I'm 2 standard deviations up, and that's how I get 70. And then if I add another standard deviation up, the third one, that's how I get to 72.5. Okay, well, what's going to happen over here on this side? On the left, when we go down, we have those negative standard deviations, so we are subtracting away 2.5. So 65 minus 2.5 is 62.5. Subtract another 2.5 and you have 60. Subtract another 2.5, oopsie, that's not 60, that's not 68.5, that is 67.5, right? 67.5. Okay, so my bad. All right, 67.5. Okay, so there's that. Now, then I labeled in my percentages. You know, you have your 68, your 95, and your 99.7. I went ahead and put all of the little small ones in there as well. Okay, so question then is, what percentage of women are taller than 65 inches? Well, that's this top half. So how could you know this percentage even if you didn't draw out the normal model? So guess what? 50% of women are taller than 65 inches. I would know this because 50% of data is above the mean and 50% of the data is below the mean. So I would have known it just because of that. How about 62.5 inches and 67.5 inches? What percent of women fall between those? From 62.5 to 67.5. Well, that's within 1 standard deviation. How do you know this? 62.5 is 1 standard deviation below the mean. 67.5 is 1 standard deviation above the mean. So according to that empirical rule, 68% of observations fall within 1 standard deviation of the mean. Therefore, 68% of women are between 62.5 and 67.5 inches tall. All right, next. How about between 60 and 70? Well, I look up here and I see that is 2 standard deviations below the mean and 2 standard deviations above the mean. So, like number 2, I've got that situation covered. 60 inches is 2 below the mean, 2 standard deviations. 70 is 2 standard deviations above the mean. According to the empirical rule, 95% of observations are within 2 standard deviations of the mean. Therefore, here's my context, 95% of women have heights between 60 and 70 inches tall. All right, so see, that's how we are being able to find the proportion of women that have certain heights. Okay? Now we're going to get a little bit more involved. Now we're going to see something such as this. What percent of women are between 60 and 67.5? So I'm going to go from 2 standard deviations down to 1 standard deviation up. And then this one, number 5, what percentage of women are shorter than 70? So I want you to pause the video for a minute, and then I want you to calculate those proportion of women that fall in those height amounts. Okay, do that now. All right, so what we find out is here with number 4, we have the 68% plus the 13.5%. So 81.5% of women are between 60 and 67.5 inches tall. Here, I could add all of these sections together, and I get 97.5% of women are shorter than 70 inches tall. All right? Now, looking at number 6, you may have computed it differently. There's 2 ways I could have done this. I could have seen I want to add together all of those pieces there, or I could say I want to do 100% and subtract off this area here. So just take off this amount, this top part. Well, according to this, that top part is 2.5%. So I could do 100% minus the 2.5%, and I get what's left, which is the 97.5%. All right. So what I want to do is I want to stop at this point because we've now just learned what the normal model is and how to compute areas and probabilities when you are landing on a whole number standard deviation. Okay? But we're about to breach into how do we do this computing if you fall into not a whole number standard deviations, like how many women are shorter than 66 inches tall. Okay, well, that's not on a whole number standard deviation. So the next video is going to address that.